Hello friends, so today we are going to solve 6 questions, and these 6 questions are somewhat, you can say, related to mass, energy and momentum. And the first question, it states that a chain of length L as and mass density rho kg per meter is held such that it hangs vertically just above a scale. It is then released. What is the reading on the scale as a function of height of the top of the chain? So we have to find out the relationship between the height, we can say the reading of the scale, and with the height of the top of the chain. Okay. So we are given, so let us start with that thing. So we are given that we have a chain of total length is capital L. So we can say that total length of chain is our capital L, and linear mass density is given as rho. Okay. And it says that initially it is just at the, you can say, above the scale, okay, at vertically, and it is released from rest. Okay. And obviously the reading of the scale is nothing but, you can say, the normal as a function of height of the top of the chain. Okay. And let us assume or denote that the height of the top of the chain above the scale let us suppose that is y of t. And so obviously we can say there will be a gravity G that will be acting downward, and in this entire discussion we are going to take downward motion as a positive. Downward we are going to take as positive. So like we said that the height of top of the chain above the scale is y of t, and total length of the chain is our L. It means the length of the chain already in the scale will be L minus y of t. So from here we can say that length of chain already on scale is our length minus y. Okay, y of t, let us assume this is nothing but our y. Okay, so it means we can divide the entire mass of the chain into two parts. First part will be depending upon the length of the chain that is just above the scale, and the second part will be the length of the chain that is on the scale. So we can say that masses of two parts, and first part we can call that as a moving part, moving part that is still falling. And let us call this as mass moving, and that will be equal to the linear mass density, that is rho, multiplied by its length, that is y. And we are having the second part, that is resting part on the scale. So you can say resting part, and that part is on the scale. And let us call this as mr. R is for rest. Then we have its linear mass density multiplied by the length that is on the scale, that is our L minus y. Now let's find out, because we need to find out the, you can say, the velocity just before, velocity of the change just before it reaches the scale. Okay. And for that we are going to use conservation of energy. So we can say that velocity of the falling chain is, we can say, we are using energy conservation. And let us suppose that velocity of falling chain is v. So as per the energy conservation, we can write it's, because it is going to start from the rest, so mgh, and h is our L minus y, will be equal to its kinetic energy, that is our half mv square. And here mass and mass cancels out, therefore we get that velocity will be equal to 2g L minus y. Okay, so this is the velocity just before it reaches the scale. Okay. So we can write this as speed of chain just before it reaches the scale. Now we got the velocity part, and from this velocity part we are going to find out, or we are going to find out what will be the scale reading. Okay, and the scale reading will be consisting of two parts, or we can say two parts are going to contribute to the scale reading. First will be the weight of the chain that is already in the scale, and second one will be the momentum flux. Okay, in the simpler term, the momentum flux is also called as a force due to stopping the incoming chain. Okay, that is, in simpler terms, is called as a momentum flux. So like we had two masses, okay, one mass was our moving part, other one of the resting part. Okay. Likewise, we are going to have the scale reading, and that scale reading will be depending on two parts. First will be the moving part, and that moving part will be giving us a momentum flux. And second part will be our resting part, that is simple, our weight, that is our mg. So we can say that contribution to scale reading, and we are going to have two contributions. First will be weight of the chain already on the scale. Weight of chain already on scale, and let us call that FW, and FW will be equal to mg, and we know that its mass is our L minus y multiplied by g. And the second contribution will be the momentum flux. Okay. And for momentum flux, first of all, we are going to find out, basically we are interested to find out the rate of change of momentum, because rate of change of momentum also gives us the force. So we are going to find a rate of change of momentum, and for rate of change of momentum we need to find out how the mass is changing when with respect to time as it lands on the scale. So this momentum flux, we can first of all find out here. First part, we are going to find out mass landing per unit time. Mass landing per unit time. That is our dm by dt. And dm by dt will be equal to our density multiplied by the velocity. And from here, we can easily find out the momentum lost per unit time. Momentum lost per unit time. And momentum will be equal to our dp by dt, and that will be equal to our, we just found out our this rate of change of the mass multiplied by the velocity. So this is a sigma v square. And we know that this rate of change of momentum is also a representation of our this force. Okay, and therefore we can say that force on the impact will be equal to our sigma v square. And if we substitute value of our square, so we get the sigma, and v square was our 2g L minus y. So this comes at 2g L minus y. Now we can easily find out the total reading on the scale. Total reading on scale. And that we can nothing but our normal, and that's dependent upon the length of the this y, whichever taken as length, will be equal to f weight plus f impact. And now we simply substitute the values, so we get our reading will be equal to, and we have this as sigma L minus y times g plus twice sigma g L minus y. Okay. And so with this gives us our 3 sigma g L minus y. So this is our reading on the scale. Okay, that is dependent upon the length of our the chain. We have to remember that L is the total length, and y we have taken as length which is not on the scale. Okay, so L minus y is a representation of the total length which is on the scale. So this is major. Okay, now we come to the second question. This second question is somewhat similar to our this first question. Okay, only this terminology is a little bit different, but the method of solving will be our same. Okay, and so we are given an empty freight car on a level railroad track has a mass m. A hole above the freight car opens and grain falls down into the car at a rate of r, measured in kilogram per second. The grain falls a vertical distance h before hitting the bed of freight car without bouncing up. How much normal force is exerted on the freight car from the rails at the time t after grain begins to hit the bed of the car. Assume the grain starts from rest. Okay. So first of all, the major difference between the two questions is that we have a rail car, okay, and it is we have a rail and that is lying on the rails. Okay, so we have to find out the normal force that the rails are exerting on the entire system. Okay, so it means we have to consider the weight of the rail freight car as well, plus the weight of the grains that are falling on it. So that is the total reaction that will be generated by the rails. Okay, so this is the major difference between the two. And here the grains are the rate of falling the grain is given as r. So indirectly this is given as dm by dt. Okay. In the first question, the mass was, you can say, dm by dt. We just calculated. Here it is given in the form of a rate. So we are given that we have a freight car and its mass is given as capital M, and we are given that the grain falls vertically at a constant mass rate. Grains fall vertically at a constant mass rate, and that mass rate is represented as our r, which will be nothing but our dm by dt. Okay. And it is also given that they are falling from the height h. Okay, constant mass rate from height h. And okay, so these are the things which are given to us, and obviously we are going to find out the normal force from the rails on the car at time t. So first of all, we are going to find out what will be the mass of the grain at time t. So we need mass of the grain in the car at time t, and we are given that it is falling at a constant rate r. Okay. Therefore we can write that mass at time t will be equal to m of t, and that is equal to r multiplied by time t. It means total mass supported by the rails. Total mass supported by the rails at time t. Total mass supported will be, let us suppose we denote this as m capital T at a certain time t, will be equal to mass of the rails, mass of the freight car, that is our m, plus mass of the grains at time t, that is our r of t. Okay. So this summation is our total mass supported by the rails at any time t. Okay. Now once again we are going to find out the speed of the grain just before the impact, like in the first question. Okay. So we are going to find out speed of grains just before impact. And for that we are going to use the conservation of energy. In the question it's mentioned that they are going to start from rest and are falling from the height h. So mgh will be equal to half mv square. So we are going to use energy conservation. And energy conservation, let us suppose that velocity is given as v. So we have this as our mgh is equal to over half mv square. And this mass and mass cancels out. Therefore from here we get that our v square is equal to over 2gh, or we can say that v is equal to square root of 2gh. This is the velocity just before the hitting the car. So you can say that this is the velocity of grain just before hitting the car. Grain just before hitting the car. Okay. And now we are going to identify the forces that will be acting on our freight car. Okay. First of all will be the weight of the freight car. Second one will be the weight of accumulated grain that is already on the freight car. And the third will be the additional force that will be used to stop the incoming grain. Okay. Or in simpler terms we can also call that force as a momentum flux. Okay. So we can say forces acting and first one is the weight of freight car. And let us call this Fc, which will be equal to mass multiplied by the acceleration due to g. And second one will be the weight accumulated because of the grain. Okay. So we can say that weight of the grain in the car. And let us call this as our Fg, where G stands for grain. That will be equal to its mass. We have found out that it's RT multiplied by G. Okay, let us call this as capital G. G for here grains. And finally is our momentum flux. Momentum flux, which is nothing but the force that will be required to stop the incoming grain. And so for the momentum flux we are going to use the momentum part. Okay, so we know that the incoming grain has a momentum and let us suppose that momentum is a p, and p will be nothing but its mass times the velocity. Okay. And from here we can easily calculate our momentum per unit time. Momentum per unit time, which is our dp by dt and that will be equal to, because mass is nothing but our, let me write it here, mass is our RT times V. Okay, so dP by dt will be giving us R times V. And it is also given in the question that these grains are not bouncing back. Okay, so we can easily find out the change in the momentum. Okay. Therefore, from here we can find out the change in momentum per second. Change in momentum per second, and let us suppose that is our delta P. Delta P will be equal to nothing but R times V. Okay, because the final momentum is at rest, which is at 0. Okay, it is not bouncing back. And so from here now we can easily find out this change in momentum is nothing but the extra downward force on the car. Okay, so you can say that extra downward force on the car. And that is equal to over, let us suppose, F impact. Let us call this as Fi. That is nothing but our delta P, which is R times V. Okay. And V we already know, it is square root of 2gh. So this comes as R and square root of 2gh. Therefore, we can say that total, you can say that the total force that will be acting on the rails will be the summation of this Fi and this Fg and Fc. Okay. So obviously the upward force that will be applied by the rails will be equal to summation of all the three. Okay. So we have three downward forces, okay, and so normal will be equal to total downward force. So we can say that normal, which is N, will be equal to total downward force. Therefore, we get N is equal to, we have our weight of the freight car plus weight because of the grain that has been accumulated or inside the car, freight car, and finally our weight, this extra downward force because of the impact, which gives us our R square root of 2gh. So this is our normal force at any time t. Okay, so we can just introduce here time t. So this is our time dependent function. And now we come to our third question. And this third question, it states that a ball of mass m rolls in a bowl bolted on a cart. The bowl and the cart moves together and have a combined mass mc as shown in the figure. Initially, the cart moves to the right with a speed v0 with respect to the ground, while the ball is at rest with respect to the cart. The ball then slides down to the bottom of the bowl. When it reaches the bottom of the bowl, it moves with a velocity vb with respect to the cart. At this instant, how fast is the cart moving with respect to the ground? Okay, so we have to take care of this, all the relative things here. Okay. Because some of the things are mentioned with respect to the ground, and some of the things are, you can say, mentioned with respect to the cart. And finally, we have to find out the answer with respect to the ground. So all these relative things should be taken care of. And the basic figure, that is, so we have a cart. Suppose this is the cart, and this to this cart we have a bowl, which is bolted. It means it is attached to it. Okay, it's not moving separately. And there is a small ball, let us suppose here, whose mass is of m. And this bowl as well as our cart is having a mass of mc, total mass of mc. Okay. And they are combined moving toward the right with the velocity of our v naught. That is given to us. Okay. And there is no friction anywhere. It's a completely frictionless. Okay. And so let us clearly define what are the things that are given to us. So first thing that is given to us, that our cart plus bowl, they combined are having a mass of, and that mass is given as capital MC. And within this we have a ball whose mass is given as small m. Okay. So we have a ball of mass, and its mass given as small m, and it is inside the bowl. Okay. And so we are also given the initial condition, and initially we are given that cart moves to the right with the speed v naught relative to the ground. Okay. So initially we are given that cart moves to right relative to ground, and the velocity is given as our v naught. Okay. And we are also given that the ball is at rest relative to the cart, and we are also given that our ball is at rest relative to the cart. And please remember, the cart and bowl are stick together. Okay, so they are not separate, they are a single entity. If the cart is moving, the bowl is moving along with it. Okay, only thing that is separate is our this bowl. Okay, it is not attached, it is free to move. Okay. And we are also given that when our ball reaches at the bottom of the ball, so let us suppose it starts from position A, and the bottom of the ball is our position B, and here the velocity is given as our VB, okay, of this ball, of this ball of mass m. So we can write that our velocity of ball at the bottom of the bowl. Okay. And it is given as VB, but that is relative to the cart. Relative to cart. And we have to remember that here this VB velocity will be entirely horizontal. Okay, so we can just plug it here, and this VB will be a horizontal velocity. Horizontal velocity. And there are no external forces acting on it, so obviously the total horizontal momentum will be conserved. Okay, because all the interaction between the bowl and the ball is internal. Okay, there is no external forces acting on it. Okay. and we have to find out the cart's velocity with respect to the ground. Okay, so we'll try to sort it out by working in the ground frame. Okay, and if the frame changes, we'll discuss that clearly, that also. Okay, so we are going to solve the question that in ground frame. Okay. So first of all, let's find out what will be the initial horizontal momentum. Initial horizontal momentum. Okay. And initially we are given in the question that the ball is rest relative to the cart. Okay. So we are given that initially our ball is at rest relative to cart. Okay. Therefore, we can say that both cart as well as our ball moves with the velocity v0 relative to the ground. So you can say both move with speed, and that speed is our v0, but now this is our relative to the ground, relative to ground, because there is no relative speed between the ball and the cart. Okay, and cart is moving with the velocity v0 with respect to the ground. Okay, so it means both the ball and the cart are moving with the velocity v0 relative to the ground. Okay. And therefore, from here we can find out the ball momentum. Okay, and please remember we are discussing only the initial part first. Okay. So we have our ball's momentum, and let us call this as our PB initial will be equal to its mass multiplied by velocity v0. And then we are going to find out cart plus ball momentum. Cart plus ball momentum. And let us call this as PC initial will be equal to, that is the mass of the cart, and multiply by the velocity with which they are moving. So therefore total initial momentum, total initial momentum, let us call this as P of I, will be equal to this PBI plus PCI. Okay, so you can write this as PBI plus PCI, and we substitute the values, so we get our initial momentum will be equal to our mass plus small m, and v0 we can take as common. So this is our initial momentum. Now we come to our final velocity, and once again we are working on the ground frame. Okay, so we have to remember this. We are discussing everything with the ground frame. Okay, but in the question we are mentioned everything in two frames. One is our cart frame, other one is a ground frame. So we have to make sure that everything aligns with the ground frame. So then comes your final velocities. And we are still working with our ground frame. And let's assume that the final velocity of the cart relative to the ground is v. You can see that final velocity of cart relative to ground, and that is our capital V. Okay. But we are given that the ball velocity relative to cart at the final velocity means at point B, okay, at this point. Okay, so we are calculating everything now at this point. So initial point was our A and final point is our B. Okay. So we can say that ball's velocity relative to cart and that is given to us as a VB. Now we can find out the ball's velocity relative to the ground. So we can find out the ball's velocity relative to the ground, and that will be equal to nothing but, let us call this as a VB capital G will be equal to the final velocity and the velocity of the ball. So this is the ball velocity relative to the ground. Now we can easily find out the respective momentum, cart momentum as well as ball momentum, because we already know their final velocities. So now we come to a final momentum. And first we are going to calculate the cart's momentum. And cart's momentum, let us call this as PC final, which is equal to its mass multiplied by velocity. And then we come our ball's momentum. And let us call this as a PB final will be equal to its mass and the velocity with respect to the ground. Now we can find out the total final momentum. And let us call this as PT final will be equal to obviously summation of the both. And so we get this as MCV plus MV plus VB, and we can just make a minor adjustment here. So we get momentum total final will be equal to, we can take V as common, so this will be MC plus small m plus m times VB. Okay. And now conservation of momentum, because all the forces that are interacting forces between the bowl, cart, everything are internal forces. There are no external forces. Therefore, we can say that our momentum conservation and which gives us that our total initial momentum will be equal to total final momentum. Now we simply substitute we get this as our MC plus m times V naught is equal to MC plus m times V plus m times VB. Okay, so we are going to solve for this capital V, which we are required to find out, and this we get that V will be equal to, this will be our mc plus m times v naught minus m times vb, and this comes as mc plus m. For the solution, we can just separate the denominator, so we get this as v naught minus m upon mc plus m times vp. So this is our final velocity of our cart in the ground frame when the ball is at the position B. Okay, it means at the bottommost point. So when the ball reaches the bottommost point, this is the final velocity of the cart. Cart means this ball and the cart are combined. Okay, only this ball is moving from A to B. Okay. So we come to our next question, and in this question it is given that a train travels at 360 km per hour on an almost straight track. The track is slightly sinusoidal with a vertical amplitude h over a 1 km distance as shown in the figure. If the maximum tolerable vertical acceleration of the train is set at 0.1 meter per second square, what is the maximum allowable size of h? So this question is basically, you can say, a combination of the maximum allowable acceleration, which we deal with when we study the block over block, and a little bit of here sinusoidal, you can say, formulas will be also used. So this is a little bit, you can say, this is quite easy to solve, but a little bit patience is required here. Okay, nothing else. So we are given, the figure is already given to us, so a complete cycle is given to us, so this is plus and minus. So obviously this 1 km is nothing but the wavelength. Okay. So we are given that wavelength of track, and that is of lambda, and that lambda is nothing but 1 km. And next we are given that the velocity of the train is given to us. Okay. So you can say the train speed is given to us as v, and that v is given as 360 km per hour. Okay. And so we can convert this into seconds, so this will be coming as 0.1 km per second. It means the time period to travel one wavelength, you can say the time period that is our capital T is equal to lambda upon v. Okay. And here this is very famous experiment also we usually study, and in that case we know that for a complete you can say the periodic motion for one periodic cycle, that is from plus to 1, this is a plus cycle, positive cycle and negative cycle. Okay. So this corresponds to one single vertical oscillation. Okay. This experiment visually, if we want to visualize, okay, and that is, so this entire, if I hang with the help of a spring, okay, so it means if I visualize this, so this will be our one full vertical oscillation. Okay, this positive as well as negative. So this will be resulting in one full vertical oscillation. So we have to remember this very important thing here. Okay. So from here we can say that one horizontal wavelength one horizontal wavelength corresponds to one full vertical oscillation. One full vertical oscillation. And therefore from here we can also say, so this is also the period of a vertical motion. Therefore we can say that this is also a period of vertical oscillation, vertical motion. So this is a important thing to remember here. Now we can easily find out our angular frequency and we can say that our angular frequency, and that is our omega, which is equal to our 2 pi upon t, and t we just wrote the formula is our lambda upon v, so this becomes lambda and this becomes our v. Okay, and we know that for a vertical simple SHM, the standard equation we already know that y of t is equal to h sine of omega t, because h is the amplitude given in this particular question. Okay, normally it is represented as a, but here a is given as h. Okay. So we can say that the vertical motion is sinusoidal with amplitude h. Therefore, we can say that for a simple harmonic motion, we can write the equation that our y of t is equal to h sine of omega t. And from here we can easily find out the acceleration. Acceleration will be nothing but the double derivative of this our y. So you can say our acceleration in y direction will be equal to double derivative of y, which will be giving us minus omega square h, and we have this as sine of omega t. So it means if you make 1:1 comparison, we can say that the maximum acceleration is our omega square h. Therefore, we can say that from here maximum acceleration, that is our a max, is equal to omega square h. But okay, let's substitute value of omega and then we come to the next part. So we get our a max will be equal to, our omega was 2 pi v upon lambda, so this comes as our 2 pi v upon lambda whole square multiplied by h. Okay. Now the question we are given that the maximum tolerable acceleration that is possible is 0.1 meter per second square. That is given in the question. Okay. So we can say that tolerable acceleration that is given, let us call this as our AT, then this AT is given to us as a 0.1 meter per second square. Okay, this is some kind of, you can say, usually we make this type of comparison with respect to our friction. We find out the maximum friction and then we find out the maximum possible friction. Okay, so we make the comparison we have with respect to the accelerations, and same with respect to the friction, because we make the comparison between the maximum friction that is available, which always our mu mg, and we either less than or greater than equal to the friction that is being produced. Okay, so same comparison we are going to make here with respect to a maximum acceleration and the tolerable acceleration. Okay. And for that we make a comparison now between the maximum acceleration as well as the tolerable acceleration, and we know that if we substitute, we can say that our maximum acceleration should be less than equal to our tolerable acceleration, and same kind of comparison we make with respect to the friction also. Okay, and we substitute our maximum acceleration, that is our 2 pi v upon lambda whole square to my h, and less than equal to 0.1. Okay, now it is quite simple, and we need to find out, one second, okay, we need to find out h. So we almost done here. So we get that our h will be our less than equal to, this comes as our 0.1, and we get this as a lambda upon 2 pi v, and this is our whole square. And velocity we already know. Okay, so we can just substitute it. So we get this less than equal to, this is our 0.1, and it is given as our 1, and this is our 2 pi, and the velocity is also our 0.1 whole square. And so this will be right. So from here we get that h is approximately our 0.25 meters. So this is some kind of tricky question, but the concept here used is same as of your friction comparison. Okay, only thing here is that we are going to make a comparison between the tolerable acceleration and the maximum value of the acceleration. Okay. And then we come to our next question. Okay, so in this question we are given a uniform rope of length L and mass M passes over a frictionless pulley and hangs with both ends at equal heights. If one end is pulled down by a distance x, then the rope is released. The acceleration of that end at this instant will be. So in this case, we can just draw an approximate figure, and we are having a pulley, and that pulley is our fixed, and across this pulley we are having a rope. Okay, and both length of the rope is equal at the both ends. Okay, so this is the basic thing that is given to us. And then one of the end is pulled. Okay, let's assume that our left end is pulled downward. Okay, and it is pulled by a distance of x. Okay. Therefore, we can just redraw this figure. So obviously the length of the rope on the left side will be on the higher side as compared to the right side, somewhat like this. Okay, so this is a basic figure, and we are given the total length of the rope is our L. Okay. So let us say that total length of rope is our L, which is not going to change. Okay. So let us call this is our initial condition and this is our final condition. Okay. Therefore we can say that total length is our L and its mass is given. Yeah, mass is given. So let us write that mass of the rope and that is our capital M. And from here let us calculate the linear mass density. Linear mass density, that's a lambda, will be equal to the total mass and total length. Okay. And so okay, next we can say that in initial case for A, okay, so we can say our initial case and initial case we can say the length of the rope on both sides will be L by 2. Okay. You can say that our length of rope on each side will be L by 2. Here in the question it should have ideally mentioned that we can just ignore the length of the rope that is along this. So each side is going to have a length of rope that is of L by 2. This is also L by 2 and this is also over L by 2. Now in the part B, we are given that the length is increased, or we can say it is pulled one end. Okay. Therefore on left side, because we said that it is pulled downward on the left side, the length becomes L by 2 plus x, and on the right side the length becomes L by 2 minus x. This is our final condition, that in figure B. So, and we are given that one end is pulled through x, and let us assume that is our left end. Therefore we can say that the left side length will be equal to L by 2 plus x, and right side length will be equal to L by 2 and minus x, and respectively we can find out the mass of both sides. So left side we can say that its mass, suppose our m left, will be equal to its density, and density is our, okay, later on we can put lambda. So this is our L by 2 plus x, and on the right side we get this as a lambda L by 2 minus x. So they are mass on the both side. Obviously left side is heavier, so it is going to move in the downward direction. And from here we can also say that the net driving force net driving force, okay, because the both sides are having now unequal masses, okay, so we can say net driving force, let us suppose that is a F, will be equal to our left side weight minus the right side, okay, because left side is our heavier now, and we substitute, so we get our F is equal to, and lambda we can substitute our m upon L, which we can take in common, so this comes as our L by 2 plus X, and this is minus L by 2 plus X, and times G. Therefore we get that the force, and here this L by 2 cancels out, therefore we get this as our 2mx L times G. So this is our net force, driving force, and we know that the total mass is of m, and from here we can find out what will be our acceleration. So we can simply equate it equal to mass into acceleration, and this mass and mass cancels out, therefore we get our acceleration A will be equal to, we get this as our 2gx upon L. So this is the acceleration. Excuse me. Okay. And now we come to the next question, and in this question it is given that the bruise threshold for a fruit is the largest height it can be dropped from rest without bruising. The bruise threshold of 0.2 kg apple on a steel is 10 cm. Suppose that it always takes 0.1 seconds after impact for the apple to fully stop, and that 4 cm square of the apple comes into contact with the surface during the impact. What is the minimum average pressure is required to cause the apple bruise? Okay. The question is language a little bit tricky, but it is quite simple. We are going to make a comparison between the threshold and the maximum value. Okay, and then we are going to get the answer. Here the comparison in terms of our pressure. Okay. And this is also, we can easily draw an analogy between the friction also. We can make a comparison between the friction, maximum friction and the threshold friction, or and that gives us the value of that friction. Okay. And in the question it is mentioned, or defined rather, that bruise threshold is the largest height without getting bruising. It means bruising means damage. Okay, there is nothing much difference between the bruising and the damage. So we have to find out the average pressure that requires for to be bruised, and for that we require, because area is given to us, we are required to find out the force. Okay. And so the things that are given to us, first thing is given to the mass of the apple, and mass of the apple, let us suppose is our m, and that is given to us as 0.2 kg. Okay. And the height of the threshold, yeah, we can say bruise threshold height, let us put that is h is also given at 10 centimeter, and we can write this is equal to 0.1 meters, and time taken to come at rest after the impact is also given. Time taken to come to rest after impact. That is our t, and that t is also given as 0.1 second. And area that will be coming in contact is also given to us, and that is our A. So you can say that area, you can say contact area rather, contact area during impact. That is our A, and that is also given a 4 centimeter square. Also we can write this as 4 into 10⁻⁻4 meter square. And we need to find out the average pressure. Average pressure, we have a requirement of force, and time is also given, so we are also going to make use of the impulse part also. Okay. And first of all, we are going to find out speed of the apple just before the impact. Okay, so for that we are going to use the conservation of energy. Speed of apple just before impact. That is given as V. Okay. And we are going to use the conservation energy. So we can say initial energy will be entirely our potential energy, which is our mgh, and final energy will be entirely the kinetic energy. Will be equal to our half m v square. And now we come to our energy conservation. And energy conservation is equal to our initial is equal to our final, which gives us that our mgh is equal to half m v square. So mass and mass cancels out. Therefore we get that the velocity just before the impact will be equal to 2gh and square root. So this is the velocity just before the impact. From here we can find out the momentum just before the impact. Momentum just before impact. Let us call that a P will be equal to mass times velocity. Okay. And so we can say our P is equal to mass square root of 2gh, and we can substitute the values. So mass is our 0.2, and this is our 2 into, let us take g as 10, and this is height is our 0.1. So we get the momentum is equal to approximately equal to our 0.282. Okay. Now it is given in the question that it comes into stop after 1 second. Okay, so we are going to use impulse momentum theorem, or we can also call that as a average force during impact. Average force during impact, or we can say this as our impulse momentum theorem. And we are given that apple comes to rest in 1 second. Okay, 1 second, 0.1 second. 0.1 second, not 1 second. So we can say that apple comes to rest in time which is 0.1 second. And so we can find out here change in momentum. Change in momentum, that is our delta P, will be equal to P minus 0, that will be giving us P. And from the theorem, which is our impulse momentum theorem, we can write that the force average multiplied by time t is nothing but our change of momentum. Therefore, we can say that our average force, that is our force average, will be equal to change in momentum divided by t. Change in momentum is a 0.28.1. So therefore, we get that our F average is equal to 2.82 Newton. So we found out our average force. Now this average force is the contact force that is responsible for bruising. Okay, and we already know the area. Okay. Therefore, it's quite simple now. So we can say average pressure on the apple. Pressure on apple, that is our P is equal to our force average upon area. So we get pressure P is equal to 2.82. This is 4 into 10 to the power minus 4. Approximately it will be coming as 7050 Pascal. Okay. So these were the, I think, 5 questions which we did today, and these 5 questions were somewhat related to your, directly or indirectly related to your conservation of momentum, or we can say the change of momentum. Okay. And okay, so this completes all the 5 questions. Thank you.